Hello everyone, hope you're doing well. On to another day of recording stuff. I want to pick up where we left off with a double slit apparatus. If the distance between the slits was d, we said that we're interested in seeing what the interference pattern looks like on the screen, distance d away. We have ray 1, ray 2, and they arrive at point P. You have path P2, path P1. And the key concept we had looked at was that what determines whether you have a maximum or a minimum constructive or destructive interference is the phase difference. And the phase difference is determined by the path difference. Because delta phi is equal to 2 pi over lambda times delta x. Remember that. Delta phi, the phase difference, is equal to 2 pi over lambda times delta x. We've seen that in sound. We've seen that in the double slit, in thin films. Wherever you have interference, this is a key concept, the relationship between path difference and phase difference. Remember here again that all the contribution to the phase difference comes from the path difference. We're not considering differences in time or the phase constant. So these two sources start out at the same time, and they are in phase. They have to be coherent. The way we guarantee that is by splitting the beam into two parts. And the reason we can do that is because the diffraction, which is what we're going to talk about today. Diffraction is where you have a wave source coming to like a wave break at sea. These two holes become secondary sources of light, and now we have two sources that can interfere, and you can see the waves from these sources can interfere, and you can see a pattern on the screen. Now, the main idea was that the path difference can be reduced to this, the path from here and there was we drop a perpendicular down to the line connecting the center here to the point P. This is perpendicular here. From here on, things are equal. So the path difference reduces to this distance here, d sine theta. For double slit apparatus is d sine theta for the path difference. For thin film, it was 2t times n, and for the Michelson interferometer, it was whatever distance difference was between the arms of the interferometer. Added to that is the extra distance the light travels in the medium, t into n minus 1 times 2. So just a quick review of the main concepts of interference and the idea that the path difference is key, and the path difference in the double slit is d sine theta. When d sine theta was equal to m lambda, we had maxima, and when d sine theta was equal to m plus a half lambda, we had minima. We're going to take this idea now and look at, we said that there is a diffraction thing happening here and there. We're going to examine that in detail. What happens to light when it goes through an aperture like this, through a hole, through a slit? This is the topic of today. We're going to tackle single slit diffraction. We're going to talk about the Rayleigh criterion, and we're going to talk about double slit interference incorporating diffraction effects. What are diffraction effects? Well, let's say that I have only a single slit, right? And you have a slit here, and it has width A. Now, remember, the slit width is less than the slit separation, the double slit. So we're going to expand this just to see what's going on here. You have a source of light here, and this becomes, light diffracts through the slit, and you end up with something interesting on the screen that we're going to look at shortly. Let's say now that I want to make this slit a bit bigger, just to give us a better idea of what's going on. Say the slit width is this much, and it's not that much really at all. Okay? Compared to the slit separation, this should be a lot smaller, but we need to be able to see what's going on. So what we're going to do is, previously we had ignored the fact that the slit had width. Okay, so it looked like that. This is the slit width. That is the slit separation. Slit separation is much bigger than the slit width. We had ignored the fact that there was a width to the slit. We considered these to be point sources, and they're not point sources. They have a finite width. So what happens when you consider the width of the slit? What we're going to do is look at, like ideally, what you want to do, let's say you're still looking at point P here. What you want to do is, over there we considered the contribution from 2 point sources over at point P. What we're going to do today is consider the contribution from each point source within the slit at point P. It's a much more complicated problem, and the proper way to do it is to integrate, and you can do that. You can look that up, how to use integrals to come up with the intensity profile over here. We're going to do something else today. We're going to do this incrementally by breaking up, excuse me, breaking up the slit into smaller segments, okay? Incremental breakup. So what I'm going to do in the first breakup is I'm going to consider that I'm going to break up the slit into 2, okay? I'm going to consider contributions from these 3 points. This is the first breakup of the slit, okay? That will result in what we call first order diffraction. So what happens here? The slit width is A, okay? And now, you know, what we had before was we have now points where the slit width is, or the distance between the sources is A over 2, while before we had D here. And you can infer where we're going with this. Remember when we had D here, we had the point here, we said, you know, the path difference boils down to D sine theta. We're going to duplicate that here as well. This is the main axis, and this is the angular position of the point P. And what I'm going to do now is use what I learned from double slit interference and diffraction. We're breaking up the slit in the first breakup into 2 equal parts. We're considering contributions from here, there, and there. The strategy is to do another breakup next time where we break up these guys into halves as well, so on and so forth. We keep breaking up the slit width into smaller segments and hopefully come up with some sort of general formula that will allow us to not use integration. Again, the best way to obtain this is with integrals, and you can look that up on your own. We're going to do it in a simpler fashion. It's going to take a little bit more work, but it might make more sense because of what we've seen from we're capitalizing on what we know, leveraging what we know from the double slit apparatus. We're using the strategy and the tactics that we used here over here to come up with a meaningful description of the diffraction pattern from a single slit. So what we're going to do now is the following. We're going to say that, well, I have sources 1 and 2 and 3, okay? First, what I'm going to do is look at the path difference between sources 1 and 2 by the time we get there. Let's say I'm only looking at, you know, there's lots of other points, but for now I'm just looking at 1 and 2 and 3. What happens when these guys interfere over there? We're going to draw a beam this way. And, well, this is our second beam here. And to find the path difference, we're going, and this is angle theta here, we're going to drop down a perpendicular from here to there. And we're going to consider this guy over here. Okay? So this is, you know, light from source 3, light from source 2, and we're going to drop down a perpendicular here as well. Okay? And we can see now, this is perpendicular, that let's consider sources 1 and 2 only. Okay? What is the path difference between, this is something you guys know. Okay? As a matter of fact, what I'd like you to do now is pause the video and see if you can come up with an expression for the path difference between 1 and 2 by the time the beams get there. Okay? By the time the beams have gotten there, ray 1 and ray 2, what is the path difference between these guys? And that is going to result in the phase difference, and that's what's going to give us maxima or minima. So please pause the video now and see if you can apply what you learned from double slits. Review double slits if you want to. See if you can apply what you learned from double slits here and come up with a meaningful expression for the path difference between 1 and 2 and then between 2 and 3. All right, folks, back to this. The path difference between these guys from our previous experience can be reduced to this distance here and that distance there. So delta x12, okay, that's this distance here, delta x12, and this is delta x23. Delta x12 is equal to what? From what we know, this is equal to that. What remains here is the extra distance that this, ray covers, and that's the path difference. And if this is theta, then we know from the Mansour rule that this is also theta, and that becomes what? A over 2 sine theta. So the path difference between 1 and 2 is A over 2 sine theta, and same way, path difference between 2 and 3 is A over 2 sine theta. Okay? And the way it turns out, finding, you can end up with a pattern on the screen. Remember, for the double slit, without looking at the slit width, what we had was something with maxima and minima, and the maxima were located at angular positions of given by d sine theta equal to m lambda, and you can look at the notes now to look at that in a bit more detail. Right? The angular, this is covered really well in the notes. This tells you that the angular positions of the maxima are given by sine theta equal to m lambda over d. Right? The diffraction pattern from a single slit is going to have maxima and minima. It just so happens that the positions of the maxima are kind of funny. Right? If you do the integrals, if you do the integration, you'll find out exactly where these maxima are. If you do the, if you want to, use this method, all we can look at is the minima. Right? The maxima are not located at full integers. I'll show you what that means in a minute. So we're looking at minima, and the minima are located where? When delta x is equal to, and we look at the first orders only. Like when you remember when we said d sine theta equals to m lambda, that gave us all the maxima, and d sine theta equal to m plus a half lambda, that gave us all the minima. In this case, we have two restrictions if we want to use this method. One is that we break up the slit as you've seen. We look at minima only, and we only look at the first order minima for each breakup. So when this is equal to lambda over 2, since we're looking at only at minima, I get a minimum. Okay, this is the diffraction minimum. This means that the first diffraction minimum occurs at a sine theta equals to lambda. Okay, so that's my first breakup. We had, higher orders would be 3 lambda over 2 and 5 lambda over 2, and this is picked up in integration. However, when we use this method, this simple method of finding out the key points of the diffraction pattern on the screen, out of those key points, we don't look at the maximum, we look only at the minima, and we look at the first order only in each breakup. That was the first breakup. Right? Now for the second breakup, what I'm going to do is, again, break up each of those slits into by half. Okay? So what I have here is, I'm going to make my slit a bit wider to allow more room for me to draw stuff in there. And what I'm going to do now is break up the slit here and break up these slits here and look at what this gives us. Okay. Now each slit width is A over 4, and you can tell from what's going on here what the path difference is going to be. As a matter of fact, why don't you now again pause and see if we can figure out the path difference between 1 and 2, 2 and 3, 3 and 4, 4 and 5. Using what you know from the double slit apparatus, while I draw some stuff here. So 1, 2, ray 3, ray 4, ray 5. Again, now guys, once you go through this is really well done in the notes, in that you can relate to what's going on with the notes hopefully after seeing this a lot better. So this will be source 1, this will be source 2, this will be source 3, this will be source 4, this will be source 5. And again, we're going to use the same technique, same trick, drop down a perpendicular from, this is the central axis, and this is the angle theta, and I drop down a perpendicular from here to there, 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 and I have these path differences now, right? They are what? This is delta x 1, 2. This is delta x 2, 3. And this is delta x 3, 4. This is delta x 4, 5, so on and so forth. What are they equal to? Well, again, if this is angle theta, then we can say that this is angle theta as well here, here or there. And the path difference, which was d sine theta up here, right? Because this was d and this was theta, right? This is theta, becomes a over 4 sine theta. So we see now that the path difference is a over 4 sine theta. And again, we are looking at the first order in destructive interference. We just look at lambda over 2, and that gives me then and this is a condition for minima, and that tells me that diffraction minimum occurs at, well, sine theta, a sine theta is equal to 2 lambda, so a sine theta is equal to 2 lambda. Remember, the first one occurred where we had, broken up the slit into 2. We had a over 2 sine theta equal to lambda over 2. That gave me that a sine theta is equal to lambda. Okay, so that was the first diffraction minimum. Okay, we're looking at minima, looking at first order. This is the first diffraction minimum from the first breakup. From the second breakup, we end up with a sine theta equal to 2 lambda, and so on and so forth. When we do the next breakup, we're going to end up with, as we continue to break up the slit, you can tell it lambda, 2 lambda. The second breakup is going to give us a sine theta equal to 3 lambda, and so on and so forth. So in general, we say that we should expect to see, we can continue with the breakup and come up with the general formula that a sine theta equal to n lambda, okay, will give me the diffraction minimum, okay, diffraction minima. This is single slit diffraction minima. Okay, so our general formula now is that, well, before it was, remember, for a double slit interference, we had, I'll write it up here just for comparison. For double slit interference, we had d sine theta equal to m lambda. M was 0, 1, 2, 1, 2, 1, 2, 2, 2, 3. Lights cut out, and lights are back. So d sine theta 3, 4, 5, whatever. Okay, that gave us the interference maxima. This was gives maxima of interference. Okay, so what do these numbers mean? Where is m equals 0? M is equal to 0. M equals 0 means central maximum right here. M equals 1 is this guy. M equals 2. M equals 3. M equals 4. So on and so forth. And the angular positions of these guys are given by what? Sine theta equal to m lambda over d. So this one sits at theta 1 equals to lambda over d, 2 lambda over d, 3 lambda over d, so on and so forth. Okay, so this was the formula we had for interference maxima. The minima are m plus a half lambda over 2, but these are maxima due to interference. Okay, when we look at the diffraction profile, these are going to be the minima due to diffraction, and n here begins at 1. So n is equal to 1, 2, 3, 4, and so on and so forth. Okay, when you actually derive what the intensity of, we derive the intensity pattern from a double slit apparatus. When you derive the intensity from a single slit apparatus, you're going to end up with something very interesting. You're going to see not something like that, like wiggly lines of equal height and equal width. Okay, more or less equal. Okay, hopefully. Right. So that's what you're supposed to see from double slit interference if the width of the slit was infinitely small, like a point source. From a single slit, however, what you're going to see is the following. You see a big envelope that looks like that. This is your intensity profile, and we'll look at the meaning of these angles now. I'll have to do a little bit for you on the double slit as well to make sure that we have covered that part. So what you end up seeing now is okay, diffraction envelope. This guy is your central envelope, main envelope, and you have subtending envelopes of light. What is theta 1 in this case? Theta 1 is this angle here, right? This will be theta 1 from diffraction, and that's a minimum, right? So that's the angular position of the first diffraction minimum, okay? And what is theta 2 diffraction is going to be this guy here. So that is theta 2 diffraction measured from here, theta 2, the angular position of the second diffraction minimum given by, so this one will be equal to, from there, sine theta is such that sine theta 1 diffraction for minima is equal to lambda over A. This guy is equal to, well, twice as much. It means that sine theta 2 diffraction is equal to 2 lambda over A, and so on and so forth. The number on the bottom here, the value on the bottom here is not D, it is A, the slit width. So the angular positions of the minima, sine theta n sub n for diffraction minima are given by n lambda over A. Okay? All right. So you can now begin to see what's going to happen when we have two slits. Okay, you'll need another bit of information before we get there, but you can kind of tell if I put another slit here, two slits, what's going to happen there more or less. Okay, get an idea of what we should be able to see. Before that, though, we've done this for diffraction. We did not really do it for interference. I kind of did it here. I want to expand this diagram here, right, and show you what goes on when we have double slit interference without regarding the width of the slit, right? So from a previous video, okay, what we saw was that if we have the screen here and we have the double slits over here, slit width was D, right? Again, you are looking at a point P, angular position theta. What you ended up with was, right, theta. I don't know, my theta or my angle. There we go. Theta, right? What we were looking at was interference from sources S1 and S2 over there. I just want to make sure I run through this with you. There is ray 1 and there is ray 2. And my point P is here. Shoot. Right. So what we had done was drop down a perpendicular from here to there and said that this is the path difference d sine theta. And when d sine theta was m lambda, we got maxima. And when d sine theta was equal to m plus a half lambda, we got minima. Okay? And what we said was, well, when the path, this is delta x, this is the path difference between 1 and 2. Okay? So for m equals 0, means that delta x is equal to 0, and at this point, because that's where the two paths are equal, I get what we call the central maximum, right? And then as we move up, well, one of the paths is going to become smaller, okay? No, if from here, if I move up, this path will become smaller, it become longer. We go from the path difference being 0, which is key, to the path difference being lambda over 2. Right? So go from maximum to minimum, and we said we're going to go see maximum, minimum, and then we get to lambda, and then 3 lambda over 2, maximum, minimum, maximum, minimum. So the diffraction, the interference pattern looked something like that. Okay, I'm going to go through that again. Right? This is too wide. They all have the same width, these guys. Okay, so right, I just want to illustrate something that I have illustrated up in the corner, but not fully, because the diagram wasn't as good. All these guys have the same width and the same height, theoretically. Again, that happens because we're ignoring the slit width. So this is your m equals 0 right here. And this is m equals 0 maximum, okay? And this is your m equals 1 maximum, and they exist on both sides, okay? So that's your m equals 1, and that's your m equals 2, and we're looking at maxima, okay? So this is the m equals 0 minimum here, okay? And that's the m equals, and so on and so forth, okay? So how do these thetas pan out in this case? So for example, what is theta? Theta 0 is this one here, okay? So theta 0. So the angular positions are given by, well, look at this. If I'm looking at maxima, right, then d sine theta equal to lambda gives me that sine theta, right, is equal to m lambda over d. Then the angular position of the 0th maximum, we call it 0th interference maximum, right, is equal to 0, right? And then we have sine theta, for example, 1 for interference maximum is given by lambda over d, so on and so forth. So in general, I'd like to add a little label to this. Sine theta sub m for interference is equal to m lambda over d. Now what do these look like? Well, what is theta 1? Theta 1 is right here, right? M equals 1. This is the m equals 1, sorry, not 0. M equals 1, M equals 1, M equals 2, M equals 2. And they're on the same side, so please fix that. Okay? So that's m equals 1 here, m equals 0, m equals 1, m equals 2, m equals 2, so on and so forth. So this angle here indicates the angular position of, we will label this as theta 1 interference to indicate that this is the angular position of the first interference maximum. And this is given by sine theta 1 interference equal to lambda over d. Okay? And so on. And this will be sine theta 2 is 2 lambda over d, 3 lambda over d, 4 lambda over d, so on and so forth. Okay? Theta 1, theta 2, theta 0, theta 1, theta 2, theta 3, theta 4, and so on and so forth. Okay? So what I'd like to do now, guys, is continue with the double slit or single slit diffraction and get into the idea of Riley's criterion after a small break.